What you doing, man?
All right.
Is this thing being video?
Yes, this one. Yeah. How's the camera, eh?
Oh.
Ready?
Is an old fella introducing another old fella?
Well,
is that right?
Yeah. I'm not older than you.
Hey,
I'm much older than you.
much older. I don't know about that.
It was nice. Went to. Ah. Oh, I can just introduce you there.
Right. So everyone else there's a few people still enjoying their pretty huge morning tea. They might be here a long time before they finish. But better get. Okay. Sorry about that. We'll start at session 2, and this is potentially the most important presentation you'll have all day, because the most important thing is failure mode assessment. And if we don't understand that, well, probably all the monitoring and surveillance we do is not going to be really worthwhile. So I'd like to introduce Malcolm Barker, who's works for GHD, and he always thinks he's nearly as old as me, but he's not quite. But he's had a lot of experience, and he's very well known and regarded in the risk assessment world. And he's going to do a presentation on failure mode assessment. So I'll pass over to Malcolm. Thank you.
Thanks, David. Yeah, okay. I have a lot of slides, way too many. So I'm going to fly. You better fly with me. Okay? Is that okay? I can't. How does this thing work? Is it going to work? It's not working.
Questions?
Yeah. There's no questions allowed? No. If you want to ask questions, just stop me and ask a question. Is that okay?
Yeah.
All right. When I say that, my name is Schultz. I know nothing. If you don't know that, then that's okay. So look, there are a lot of guidelines, standards about failure modes. They're listed there. I'm not going to go through them. I am going to basically talk about the CDA, USBR, a bit of FERC, ICMM or GISTM and ANCOLD. Just brief some of the things associated with that. So what are the statistics telling us, really? You can see there the difference between TSF and water. You see how the TSF is on the left-hand side and the water is on the right-hand side. So there's a lot more overtopping failures from TSFs. Or sorry, they're very similar to water. A lot more slope instability, obviously, because of all the static liquefaction and the things we've been talking about. And earthquake instability for TSFs is much higher, which is understandable. But seepage erosion is much less in tailings storage facilities. And I said to a couple of guys recently, I said, do you want to do a PhD? Do a PhD on piping of liquefied materials through cracks in a TSF. See if you can actually get it to work. Nobody's done that, as far as I'm aware, of the actual liquefied tailings. So we've seen that figure there, which is basically the surveillance from Bulletin 138. Where do we fit in? Well, you can see it there with surveillance. Obviously, you've got your monitoring and your visual inspections, which we've talked about. I'm not going to go through that. So really, according to B138, which I think Caius did actually, it's the pinnacle. Maybe it was Caius said that. It's really important in terms of the monitoring with instruments, which is what we're going to be talking about. But as Kaya said, visual and Manuel as well, visual is super critical. Don't ever forget visual as being a tool, as being an actual piece of equipment. Your eyes are better than many equipment. So why monitor? Kaya said that we can potential site failure modes, damage, changes, and design intent. I'm going to go through a bit of philosophical mumbo jumbo now, okay? So be careful now. when we talk about inductive and deductive reasoning, who understands that? Can you put your hands up if you understand that? Who understands deductive and inductive reasoning? Thank you. I'm in the same boat. So inductive reasoning uses a whole bunch of specific instances and uses them to get a general conclusion. Whereas deductive, Sherlock Holmes was a deductive. He deduced things, right? As a man who would try and find out who committed a crime. But it takes general statements and premises and uses them to propose a specific conclusion. If you don't understand that, don't worry. So when we conduct a failure modes analysis, we can use both inductive and deductive reasoning. You probably do it without realizing what you're doing, by the way. So this is deductive. You start with general principles. You apply to specific cases. For example, there's a general principle. Structural weakness can lead to dam failure. That's a principle, right? So a specific case, you're inspecting a dam for known structural weaknesses and you find cracks, material degradation. Your conclusion, if these weaknesses are found, they are identified as potential failure modes. You've deduced this is a problem, therefore something's going to happen, right? That's what you've deduced. So in the failure modes analysis, you start with the unwanted event down here and you move upwards to lead to uncontrolled release of the tailings storage facilities. You'll see some diagrams which are coming up shortly, but you've got to obviously got to understand the dam components, their functions. Function is a critical part of the FMEA, both the system and the subsystem. So in other words, what is the function of a sand filter? Somebody tell me, what's the function of a sand filter? Anybody? It's for piping. What is it? It's actually for seepage control and for piping control, right? That's the functions of a filter in a dam. So you have to understand the function so you can define a failure mode. How does that fail in what it's supposed to do? And what does that mean in terms of the end result, right? And they're obviously complex. The more detailed your system is, the more and more complex things become. Inductive reasoning, which is what most people here probably do. Who does event tree analysis here? Anybody? When you're working out this happens, and this happens, and this happens, and off you go. That's inductive reasoning, right? You're actually starting with a specific observation. I've got an earthquake. I've got a flood. I've got a wind, something. What happens next? So you've gathered that data and understanding from a whole lot of examples, a whole lot of data that you've got, and you can start to reason what's going to happen next. That's what inductive reasoning is. Here's one, for example. Several dams with similar designs have failed due to seepage. That's an observation. So therefore, the conclusion, dams with design are likely to have seepage issues, which should be considered a potential failure mode. So you've got to have, if you've got a potential, this type of dam, it's failed, therefore, when you design your dam, you better be careful. You've got to get it right. Otherwise, you could have the same failure mode, right? Like liquefaction. You're pretty stupid to not try and do something if you know you've got a problem with liquefaction, right? So PFMA, now this is where there's an argument between Canadian Dam Association, ICOLD, and the rest of the world, basically. They reckon that PFMA is a lot of, no, I wouldn't say that. They don't think that PFMA is that good, whereas the method that's in ICOLD and in CDA that's being pushed forward now is the way to go. And they are very good, I must say that, all right? And they have different purposes, and when I've been studying for this, I've realized, okay, I can handle that. But the inductive method relies on group brainstorming, and Andy called it brain sailing when he presented this. Part of this has come from his presentations to CDA. And it starts with a hazard, your initiating event, ending in the unwanted event, a failure. So what might happen if a dam experiences a large earthquake, which is a hazard, for example? What happens next? And you brainstorm that. And I know when we were doing the Oroville Dam failure or incident, not dam failure, incident, they spent a huge amount of time working on failure modes. I mean, that was seriously 2 weeks or something, I think, with David Bowles and other brainiacs in there. And I thought, man, my brain would be fried if I went for 2 weeks. 1 day is enough. Thank you very much. Right. But it's a serious amount of brainstorming. It's simple. It's commonly used. You need prior understanding of the hazards to understand what's going on. But you can combine both. So the comprehensive analysis using deductive and inductive reasoning. So while there's this conflict going up between different parties, there's no reason why they can't be both used. They are very useful in different ways. So Winston Churchill said, true genius resides in the capacity for evaluation of uncertain, hazardous, and conflicting information, which is what we're trying to do. So here's some failure mode definitions from ICOLD and COLD CDA. There is a subtle difference in CDA. A failure mode is the state or condition or loss of function or deviation from intended state, whereas the other ones, a way a failure can occur. So it's how does this thing occur? Whereas the other one's a functional thing, CDA, which is not quite the same as ANCOLD. And ICOLD is similar in the tailings dam safety. So it does say that a term failure means loss of function, ability for it to actually perform properly. So when you're doing a failure modes analysis, you've got to look at all of your stuff in your dam and think, what's the function of this thing and how will that function fail? If it fails, what happens next? You get me? So here's the CDA approach, and ICOLD, by the way. They have only two failure modes. Dam fails by overtopping. Dam fails through loss of strength. That's what they call a top event. This is overarching everything, right? But then the dam fails by overtopping. It's because they haven't got enough discharge capacity or available discharge capacity, installed or available, and inadequate freeboard. Then through loss of strength, there's stability, water tightness, and durability cracking. That is it. It's very simple, but we'll get into more detail on that one there. So this is an important definition on the bottom there. The failure mechanism, the process that manifests itself in an undesirable outcome. So you start with the initiator and you end with system failure, the top level system failure. And I'll show you what that looks like. So in the FMA methodology, you describe your system really clearly, you understand its function of everything in your system. The system might be a dam or dams or spillway or outlet works or whatever it is. You've got to be able to define that clearly so you can actually work out what the functions and the failures might be. They say create a block diagram. I prefer a functional diagram. What's the function of this thing? I mean, typically you guys would probably draw, here's my dam, here's my outlet works, here's my filters, here's all this stuff. That's a diagram of the dam, right? So then what's the function of each one of those things inside the dam is useful. And you list them and their functions, you identify the failure modes, the manner in which a component could fail. And they've developed what's called the HFMM, which is, we'll come to hazard failure matrix. And it assists you and describes the effects, and then you likely causes, and you get your actions from that. That is actually very similar to the inductive reasoning, which we normally do with event trees. So this is what information they would give you need to get. Failure mode ID, what's the system, what's the component, the function, the failure mode, initiating event, describe the failure mechanism, and then what's the failure effect, what is it, catastrophic. So this is the typical failure mode mechanism example. If you look at on the left-hand side there, you'll see you've got an initiating event. I think it's a spanner dropping on a gauge which fails, and then it leads into the next failure mode, next failure mode, next failure mode, and eventually you get downstream flooding when the earth dam overtops because something's failed and caused a whole lot of things. You know the Swiss cheese theory that you've got to have everything lining up before everything goes bad? Well, it's kind of like this, where you say, I've got the pressure relief doesn't work, pump fails, nobody fixes it up, the spillway doesn't work, reservoir rises, and the dam overtops. Bang, 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 going from the bottom up. And there's a deductive reasoning risk on the right-hand side there. That is a picture. So you start, if you look at this diagram, you see the bottom there, you've got progressive saturation, increased pore pressure, loss of foundation shear resistance, loss of shear resistance. So it could be an all. When you're dealing with fault, this is a fault tree, by the way, as opposed to an event tree. Everybody's used to these events happening and going everywhere. This is a fault tree. So you move from the bottom up. All these things down here would be things that are not good. Then you work your way up as to what that means. And then you get slope instability, overtopping, loss of freeboard, and dam failure. That's a top event. And all of these things down here lead to that. Right? Does that make sense? Okay, simple, isn't it? Not really. When you do this, you must be careful. I've worked with fault tree analysis, and you've got to have a clear description. What is this top event here? That defines everything that happens underneath here. So you start from there and you move downwards. Overtopping by loss of freeboard. How does that happen? Oh, I've got local settlement or I've got slope instability. How does local settlement occur? Oh, I have a sinkhole or I have gross enlargement. You would need to then say, well, how does a sinkhole happen? Oh, I go down here. You know what I mean? You're progressing downward, 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 down until you come to the bottom down there where you say that is what's called an event. That's an initiating event that moves upwards to your failure, right? And when you're dealing with fault tree analysis, the immediate cause concept means I have to look immediately what happens next, then what happens next, what happens next. You can't say, oh, that happens, and by the way, that happens down here somewhere. You can't jump, for example, from overtopping by loss of freeboard to, oh, I've lost shear resistance. Something's got to happen in between the two to get to where you are. I hope you're all following me. There's no miracle rules. You can't say, oh, that'll never happen. Sorry, put it down. It may happen. And you need to understand your gate operating rules, which is an OR gate or an AND gate. These things happening together. This one means this one, or this one, and this one must appear together. So it's not straightforward. This is what I developed for static liquefaction when I was trying to figure it out at the dam that I was working on. And I thought, oh, gee, how do I get static? What are the triggers for static liquefaction? We've been talking about it, right? This is my simplistic diagram for static liquefaction. Take it or leave it. It's not necessarily correct. It's something that shows you what needs to happen to go from the top down, down, down. Is it contractive? It needs to be brittle and ductile. You get static liquefaction if it's ductile. If it's brittle, it triggers there, down there, overtopping, high pore pressure, creep, progressive failure. All those things would be triggers that take it up that way. If it's ductile, it's much less likely to liquefy, unlikely. If it's dilatant, it's also not possible. That's the deductive reasoning going down, right? And this is what was used in the Samarco fault tree. They called it a fault tree. It's kind of like that, but you can see what's going on there in terms of the events down here, the trigger mechanisms that they said would cause the liquefaction in the end for Samarco. So functional diagrams, I think, are really useful, and it clearly shows your components. Here's one, for example. You can see that's your dam. You can see how they've actually said, for example, that is a drop in its spillway there. And what is its function? For flood release, right? With air supply to prevent negative pressures. Now, you could go deeper into that. You say, well, how's the air being supplied? Could that be at fault? If the air is not supplied, I get cavitation. If cavitation happens, then I get damage. If damage happens, I can fail the dam. Does that make sense? Going down, 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 right? And this is just a tabulated thing for all those different components in the dam. So functional diagrams, there's also elemental, functional, dynamic, operational, analytic. I'm not going through these. These are all in the Canadian Dam Association bulletin in their bulletin they produced. But some of the USBR say, and I think it's quite correct, if you cannot draw the failure mode, then it's not credible. How's that one, eh? Is that putting my neck on the block, right? If you cannot envisage and even draw this thing and say, this is going to happen, that's what's going to happen, then how is it going to happen? Is it not credible? FERC have their own guidelines for that too, but we'll come to that. And so does GISTM, which we'll come to just now. So that's an analytical functional diagram. Also, we do those as a matter of course. They're obvious, right? When you're trying to analyze your dam. This is functional information table where you have your failure mode, overtopping a component, spillway, initiating event, earthquake. What's the failure mechanism that's happening to give you that failure mode for overtopping? To me, that is that's almost the same as what I would do with an event tree. The seismic happen causes it. So you can see the failure mechanism there, clearly spelled out there. What gets back to there? So you're kind of going backwards there. Anyway, that's what they do as well. But that is in the ICOL bulletin 154 and the Canadian Dam Association. That is all a fault tree. See that there? the struck dam failure because of those two failure modes. Two failure modes only, 104 combinations of hazards and failure modes. Right? So you take that nice pretty picture and you convert it into a table like that. Right? And you look at that table, you say, my goodness, that's a wonderful table. But you have to go through every single one of those blocks in this approach to figure out which of these failure modes could happen. You can't read any of it, I know that, but that's okay. But they're generic hazard and failure mode matrix. It's a good matrix, but they don't say that's not the be all and end all. When you've done the failure modes evaluation with that, and every time you got one of these, there's a question to answer. You see a little red thing up there, you know, with Excel, you've got a question there, you have to answer the question. Is this applicable? Could this happen? And it's a good way of actually prompting you to think, gee, could it happen? I don't know. Whereas when you're doing the inductive method, the way that the PFMA thing, you don't have that table. You start from, this is what I've got in my dam, this is how it could fail, and you work through that way. So as a basis for asking questions, it's really good. That's just a difference between on the right-hand side, is the failure modes analysis approach, CDA is saying. On the left-hand side is the PFMA approach, right? So you can see that seepage through the varved clay layer, and you've got uncontrolled release over here. There's uncontrolled backward erosions there. Initiating event is seepage into sand lens, and these are different failure integrity, failure of that. Very similar to that. So I do struggle understand why the CDA gets so twitchy with us in the PFMA. But anyway, that's what they say, that this is much better in terms of understanding. I really like the functional diagrams, the matrix, and even drawing up a fault tree type of approach. They can be very hard though at times. So Morgenstern in 2018, he introduced the RPN, which is the way that you get, he says you've got the likelihood, severity, and detection. Can you detect this thing? To come up with a risk priority number. And you use that when you're actually implementing mitigated measures. You could use that actually very much so for instrumentation. I have an RPN of this and that. I need to figure it out. I need to monitor that because it's too high. For example, here, you've got a red. So you say, I'm going to do something about that. But how are you going to monitor that failure mode to make sure that you understand it? Is there an instrument you can put in there that will monitor that properly? And is it visual? Is it some kind of piezometer or whatever it might be? So the RPN does help you in terms of understanding what you need to do. Then we come to Anfold, and it's an inductive method. We clearly say inductive, right? Particular faults are postulated, and the analysis reveals the full range of effects. What happened next, right? And it can be extended to FOMICA, which is a criticality analysis similar to the RPN, but not quite the same. So our process is also similar, I think, to the FMA or to the failure modes from CDA, where you agree a criticality system if you're going to have it, which is trying to define the risk, define the system, the components, and then you basically have, it must be context specific. It's going to be defined. Is a complete dam or is it an individual piece of equipment? It can be as small or as big as you need it to be. That's the definition of a system. Simple one. Not everything. That's just basically the dam is defined there. That's the system for the dam, and you work up there. And all of these would have their own system definition below that. And then, given the component number, what's its primary and other functions? We clearly say in ANCOLD, you need to define what is its primary and other functions, and then you can identify your failure modes associated with those things not working properly. And you look at your local and end effect, and can you detect it? And that's important. Can you detect it? Can you mitigate it? And what are the consequences? And detection is really critical from the point of view of your top. Right? If you can't detect it, you have no chance of warning people downstream. But you need to have ways of detecting different failure modes. So what is the best way of actually detecting that this thing is going to happen? And what can you do about it? That is a typical initiating an event spreadsheet that we use. We got all of these events down here. Some of them are crazy. For example, ice in Australia. Are you kidding me? No, we do have ice, but not much, you know. Norway, you've got lots of ice, I'm sure. But in India, I don't think you've got much ice here either. But anyway, so north, yeah, of course you would. There are lots up there, nice and cool. Okay. So, and there are things like termites. Termites are a hazard in your dam. I've seen a termite failure of a dam starting, and my boss put his finger in the hole to stop it. Right? He literally put his hand on top to try and stop this piping occurring. Right? So there are a lot of hazards you can have there, initiating events. Then the next part is your components. You can see there are a whole bunch of components in a dam. Right, there they are. There's the function, and there would be an auxiliary function over here if there are other functions. So component definition is really critical. Then well, that's the spillway components, for example, and you can see there are a few with auxiliary functions as well. And then you come to the typical failure modes analysis, and I'm going to flip over this one because there's a much better one with the USBR and Army Corps of Engineers definition of failure modes. So here we go. They clearly say you've got to describe your failure mode properly. For example, if you say piping from the embankment into the foundation, that's a failure mode, right? I mean, smiling at me thinking, oh, dummy, of course, yeah. I mean, but yeah, that's a simple definition, isn't it? What else do you need? Well, you need to know exactly how that failure mode is actually going to occur, which is why you've got this super long definition or discussion over here as to how that failure mode will occur. And when you do your exercise, you better be sure that you can describe how your failure modes are going to occur so that you can monitor them or you can control them somehow, right? If I know that I've got a failure mode that's going to be from piping or whatever it might be, it's going to get bigger and bigger, can I monitor that? Piping is a bit of a pain, actually, because it's not easy to monitor piping. I had an incident on a dam, and I'll show you just now. The pore pressure on a piezometer just went up, stopped, went up, stopped, went up, until I blew the whistle. I said, something's happening. And we found a hole in the dam. Water was squirting in there and pressurizing 200 meters away. Right? And eventually we found the hole, we fixed it. But the piezometer was telling me what was going on. I thought, wow, that's amazing. I've never seen that before like that. It was just so good. Actually, terrible, but that was good, you know. That's another way of actually describing that same event there, down the bottom there, with an inventory process, right? Just showing how it can occur, which is much easier to equate or understand, basically, as far as I go. This is FERC, where you can have different failure modes. You can either say there's not enough information, go and find it out, or can you rule it out? But you've got to justify it really clearly. And it's negligible, clearly negligible, or it needs urgent attention. So that's a FERC process for understanding your failure modes. So if you had failure modes that you realized you are negligible, can you say, I don't have to monitor it? Can you clearly be sure I don't have to monitor that failure mode? Maybe. That's your decision, right? You're the engineer. You've got to figure out, can I not monitor this failure mode? So then you've got this is the whole thing of credible failure modes. Are they technically feasible? I do like this, actually, in a way. It's kind of an interesting definition. I thought, yeah, crazy, man. You've got to have everything credible. But no, technically feasible failure mechanisms. That's the kind of thing, can you draw this thing, right? That's the way I look at it. And then the materials are present and the foundation, the properties of the materials, the configuration of the structure, the drainage conditions. You're taking account of all those things when you're evaluating the technical feasibility. In other words, if I haven't got liquefiable material, then liquefaction is not an issue, right? It's disappeared. So that's why you change the dam design from an upstream raise to a downstream raise. Simple, problem gone. Eliminate the risk. I don't have to monitor that anymore. I still have to monitor the dam zone. But they do result in different failure scenarios. So you have piping or flood overtopping or side liquefaction. So there is credible failure modes do vary with time. You know that. So we just need to be aware of that and be sure that we have And there's two words they use here which are really important. One is it's robust, and another one is not there anymore. It was there. Resilient. So they need to be resilient and robust. Robust. Resilient, it can handle changes, and robust as well. There's a definition of those, but that's what just them have got. And then you've got ICOLD. These are in the ICOLD bulletin. How much time have we got? About 5 minutes?
Yep.
Okay. Well, I got actually 0.
That's all right.
Okay. I'm not going to go through these in detail, but this is directly out of ICOLD, out of the bulletin, 194. All I've done is I've gone through and said, right, these are instability due to foundation failure. You can see all of the reasons why you might have instability in the foundation, right? There's poor pressure generation, artesian pore pressure, liquefaction, incorrect seismic hazard, erosion of the toe, or even excavation of the toe. We've had that before, haven't we, Edgar? Or there's an undetected weak materials or wrong. Those are all reasons why it might happen, right? So what are you going to do about it for your monitoring? Or there could be dam slope, instability of the dam slope. So all of those reasons might be there as to why that can happen. And then the next one, that's how you can monitor it. Maybe, for example, I'm saying if you put piezometers in, you can monitoring for seepage or blowout or heave, where you're seeing the change of pressure. Where do you put them? In the foundation, downstream, below the lower permeable layers. Those are the kind of things you've got to think about when you're looking at the failure modes. What method is there to actually monitor it, and where do you put it? We know that, right? That's what your exercise is going to be about. But first, you got to define the failure modes. What about overtopping? We talked about freeboard. There's your freeboard up there, a little bit of freeboard up there. When your flood comes up and you've got to your maximum flood level, the spillway there, you've got a bit of dry freeboard there, and then it starts to overtop. And your tailings are deposited nicely on the upstream face there. But can it be initiated by a whole bunch of things? Yes. Large floods, wind, waves, sabotage. We haven't talked about sabotage or vandalism or terrorism. It could happen, right? How do you put an annual probability there? I have no idea. But you still can put it down and say, the political climate's really bad. What do I need to do about this in my dams, wherever they might be? They're not soft targets. It's hard to destroy a dam, very hard. So what about overtopping? How can you instrument overtopping? You can check where your decant pond is. You can check the status of leak detection systems. Secondary containment. What about automatic flow measurement and fault alarms and the pumping pipeline? All those things you can monitor to make sure that everything's going all right. If they're not working, suddenly the water level goes up and you're in trouble. That's just a pretty chart showing erosion classification for different depths and that sort of thing. And in piping, as I said, the only time you get really piping in tailings facilities, as far as I'm concerned, is when the water level goes above the tailings level, and you've got that water against the embankment as opposed to tailings. So how can you monitor it? You can look at trends, rainfall, linear increasing, sudden changes. That's the one I was talking about there. You see my nice piezometer there, that orange thing? Going up nicely. I thought, oh, good, it's going to, no, it didn't, it went up. And now it's going to be fine, isn't it? No, it didn't, it went up again. Oh, now it's going to be fine. I triggered it there. I said, that's it. I've had enough of this. I need to figure out what's going on. And I found out the problem. So what about seepage? Your chemistry, we're talking about dirty water stuff. So what about measuring that in terms of, is it increasing? Are they changing? Do I have clear water now? I've got dirty water. What's going on in terms of the actual water that's coming out? And I guess visual. Remember I said visual is important. So where is it green or not green? Where is it dead or not dead? Seepage will kill as well as give life, right? Depending on what the chemicals are in the water. And environmental effects. So you've got that, we talked a little bit about it, what would be the, you're releasing into the environment during storms or seepage barriers. So your seepage barrier is the cut-off trench, for example, or the foundation grouting or something to stop the seepage. And if that fails, well, off you go. Can you monitor that? Yes, of course you can. And there's your instruments, again, visual and seepage monitoring. And that is a decision tree from John Smartfield, USBR, which he used to try and define instruments. In other words, you go through the whole process. If you want the reference for that, I can give it to you. It's a good reference to try and understand, can I chuck this instrument away? Is it useful? Where do I put it? And there's another chart to say, if I put the instrument in here, am I actually going to induce a failure or not? So you've got to be careful. You start putting an auger, or you put a hole down the middle of your dam, you could induce the failure. So you've got to be careful of that. So that's a really useful way of figuring out the use of instruments in your dam. And that is not the end. Somewhere. This thing died, by the way. It's just dead. That's done with that. That's it. Thank you. Oh, no questions, huh?
Oh, come back. Well, I think we have got a bit of time later on the end for our exercise, but we haven't actually got the sheets for the exercise yet. So I think it's probably got a few more minutes. We could take up a couple of questions for Malcolm. So anyone got any questions for Malcolm? One?
No, I'm not answering that one.
It's more of a discussion point and really a topic that we are not handling properly nowadays still. When we look at a new tailings storage facility, we need to look at it as a system. And we need to look at what can go wrong also from the operational side, not only from a design perspective, right?
Mm-hmm.
The topic that I discussed in the past a few times, and I would like to get your opinion, is the $1 million question related to human error.
Oh, yeah.
And how do we include human error in an FMEA? The tough one.
Yep. Sure.
And just, I think many people from across the world would know, and I may be wrong, but Oroville was error.
Yep.
In the water, in the hydropower space, Bayonne was a human error. Malpasset was a human error. So how do we cover this topic?
Sure.
Risk assessment. I'm not expecting an answer in 2 minutes, but
I give you one in
it's a
30
point of
seconds.
discussion that is very
Sure.
critical in the industry.
Yeah, yeah.
worldwide.
And the process that was in there for the ICOL and CDA, they do have some human error stuff in there, but you can put it into your inventory, for example. When you look at a failure mode, you describe it and you say, well, they didn't take readings, or they failed to take the readings, and the pore pressure went up, and then it failed, whatever the reason, or then the slope failed, but it would have to be a really, it's not just one measurement they failed to take, but, oh, this is really bad. They haven't taken it for a while, and it suddenly goes off. So you can introduce it in your failure mode description, understand what is going on. Operation is absolutely significant there, where, they were putting the tailings over there and they didn't stop putting it over there. And so suddenly everything went wrong. They haven't done a tailings management plan properly. So they've overtopped and the tailings went. We've had a case where tailings went over the top of a dam. It wasn't a big incident, but my goodness, the regulator got excited. Ooh. He shut them down. He said, you guys, you better sort yourselves out. You've let tailings go out of your dam. It didn't go anywhere. It just went like across the crest of the dam, but he was not happy. The guy really jumped all over them. And it's really critical, the operation, to get it right there, yeah. But yeah, human error, it's definitely in there in terms of your fault tree analysis. When you talk about spillway systems reliability, you've always got human error. The guy didn't get to site on time. Why didn't he get to site on time? Oh, the roads were blocked. Why were the roads blocked? Oh, there's a great storm. Oh, hang on. And you can go through and say, right, that's what happened. Why eventually the gates didn't work and the thing failed, right? So that's the power of a fault tree analysis. It's very powerful.
I would have just a couple of additional comments following Kai's comment and your comments too. One is that we should not be afraid of addressing operational failure. I think many of our colleagues are reluctant, and they even we explicitly say operational failure modes are not included. So we should not be really afraid of it because they're really important. And so we should really explicitly including them. And when we have problems, of course, with any type of hydromechanical equipment, it is a big thing. And fault trees and event trees, sorry. Sorry, maybe this way. So I was just saying that we should not be afraid to include operational failure modes in our analysis. And oftentimes we are reluctant to include them because it's really the human factor. It's also maybe telling the dam owner things are not being done well. And so sometimes we don't want to really go into that arena, but we should really consider that. We have good statistics of failure modes that included that happened because of human error. So that's a good anchoring. When we assess probabilities, we always use historical data to kind of benchmark and see where we are. But then with both fault trees and event trees, we can really account for the human error and break it down and then use expert judgment. So you can always analyze, is there proper training within this organization? How is the governance? So do we have procedures? Do we have a good regulation backing up the operations in this area, in this country, and for this dam owner? Do we have all the procedures? Do we have the O&M operation and maintenance manuals? Do we have the emergency action plans? So all of that really informs how we assess the human error. And we should go for it.
And that's included when we reduce risk as low as reasonably practicable. That's the GISTM term, right? And in the dams, which has been around before GISTM came along, we have to include that sort of thing. Can I improve is my operational maintenance deficient in that area? I need to fix it. It's a small thing, but I need to fix it, whatever it might be. Yeah, exactly.
It's easier said than done. You agree? And we are humans. We cannot predict each and every error that can happen in the next 10 years.
Sure.
It can be something as fine as the operation is hiring somebody who maybe is younger and there's pressure from the management and that person makes the wrong decision. We can't predict that. Or,
Sure.
We look back at Oroville. I mean, Oroville had all the expertise in the world, had all the money in the world, had amazing engineering, and one little thing slipped off, right? So it's even in a very robust organization, you can still have these things. So yeah, no, I don't disagree with you. It's just it's easier said than done, and it's still something we work on. And my point is, independent reviews are the best thing that can, dam safety reviews, review boards, etc., are the ones that are having multiple layers of independent perspective and opinion on what's happening. That could help mitigate some of the.
And I think going along with that, I didn't put a slide in here, but one of the biggest issues with all of these techniques is biases. Everybody has a bias. I think cheese is green, you think it's orange. Well, I don't care what color it is, it's cheese. And everybody has, well, I'm better than you. And come on, who's better than who? I mean, really, we got to be so careful of professional biases when we do these things. Somebody will stand up and he's the bee's knees, he knows everything, and everybody else just says, oh yeah, okay, fine. And meanwhile, hang on, this person over here who knows very little might say, but hang on. So you really got to be careful of biases when you're doing all of this stuff. It's dangerous to not. And that I've just brought that back up again because when you deal with these things at the bottom, to try and figure out what's the controlling one. If you quantified a fault tree analysis, which we do for risk analysis for spillways, you need to find out what's my critical failure pathway, right? And we call them critical cut sets. Very useful where you can figure out this went wrong, that went wrong, that went wrong, and that's why it failed. Extremely powerful. When you're dealing with the CDA approach, you may miss some of the individual mechanisms of initiating a crack, for example. Whereas in the piping toolbox, which is a pain because there's 28 of these things, you got to work through and see where is this failure mode going to initiate? How does it initiate? You can bring it into that fault tree, but it's a lot more work as well. So there are pros and cons. There's nothing's perfect, right? Combine the two together, and away you go. Okay.
Oh, hang on.
I'm gonna shut up.
Sensitivity analysis as well.
Yeah, good.
And,
Yeah.
and then it's dynamic, so you have to revisit that.
Yeah.
Every 5 years or, because it's changing and it's no different.
Yeah.
Right, so I think we cut you guys off for a minute
Yes. So we get-
and just have that one question there. Very long.
So PFMA and FBA is obviously also used to determine what the consequences. But requirement 2.3 of like JSTM, which you did cover in your slides there, says you must obviously have a consequence for credible failure modes.
Correct.
Now, credible failure modes is not associated to the probability of events occurring.
Correct.
But PFMAs and FBAs, the likelihood is considered. So what this means is that from doing consequence analyses, let's say for tailings dams, you have to, for ICMM compliance clients, you need to comply to GSTM. Therefore, your credible failure modes that you are providing consequence for may be very unlikely. And that's sometimes a very sensitive topic because inundations for something that's very unlikely is your RMF, PMP happening, and you have a catastrophic failure at the same time. Those two events, the likelihood of that happening is close to nothing. It's approaching infinity. But GSTM states that, irrespective of probability, and it's not a reflection of the safety of your facility. But from someone who's doing consequence assessments, it's challenging because I don't feel that it's necessary to analyze these events and show these massive inundations, massive consequences, because I know that the probability of it being this severe is felt, and that's where I think JSTM is missing something. In terms of credible failure modes and consequence assessments, I feel like they need to incorporate more of the PFM, the failure modes analyses, which looks at likelihood into the GSTM. So maybe just comment or think for discussion is what I'll do.
Yeah, look, I mean, when in Australia, when we deal with what's called a failure impact assessment, we look at EMF, sunny day failure, normal, and anything in between to come up with the maximum consequence. But always, when it comes to the top, you've got to think about, hang on, if that event, if I'm getting up to there, I need to warn all those people in that area. I've got to get them out. That's, I guess, where you'd say, well, yeah, I agree with you. The likelihood might be la la land somewhere. But the fact is that if that happened and you're in front of the judge, he says, no, excuse me, you knew that was going to happen because you knew there was the mapping. Why didn't you do it? Well, why? Your neck is on the block. And that's the serious danger we have now with litigation. Man alive, it's scary. And I guess I agree that the likelihood is kind of so low, why bother? But the why bother is because in the event that thing happened, if the Swiss cheese happened and that thing actually went, and you got no leg to stand on if you just ignored it or just said. But having said that, I mean, you saw that FERC allows you to take failure modes out. Even GSTM allows you to take failure modes. You think, wow, we're killing these things. And we would allow that. In terms of risk analysis, yes. But in terms of top, no. I think you still got to understand where am I going with my trigger action in terms of the responsibility as an engineer. I know does that make sense?
Yeah.
All right.
I'm out of here.
Leave the stage, please.
Thank you.
Thanks, Malcolm. So obviously Malcolm has a pretty good set of slides there. And one thing we haven't mentioned to you is that at the end of this workshop or short course, we'll be collating all the slides and making a PDF and sending you all links so you can download copies of the presentations. So I'll now pass on to Edgar. So Edgar Salas is a technical director of GHD, and he's involved in the Tasmanian energy and resources team, and he's had lots of experience in tailings dam design and construction from across South America, South Africa, Papua New Guinea, and Australia. So, there you go. Over to you.
Thank you, David. I'm just gonna go through just linking all that mechanical behavior and to monitoring performance. I think the key of all this is we went through the failure modes. We went through all the what we need to look for in a dam, the components for a failure mode, how the dam could fail, and now we need to work out what we need to actually check, read, or understand, and what values we're going to use for a failure mode. I mean, if we're talking about permeabilities, what is the permeability? How much water are we expecting to see? If we are talking about dilative, contractive, we're talking about strain. I mean, that is where we are now trying to take this to. Now, we have basically 4 questions in there, and I have basically a dam in there with a lot of instrumentation that are meaningless because you can see that it's everywhere. Then the first question is what we want to test. I mean, what is exactly what material and how we want to do it. Why we want to test it? Because it might be that it's a material in there that is completely meaningless and it's not going to do, it's not important for our dam. How can we do it? And I'm going to go through something simple in there. And what happened next? Then hopefully we can actually go through these 4 questions and get an answer. Then this is it's going through different, let me just see how this works. Yeah, different dams in here and different components. I'm trying to answer that question, what we want to test. Then this is a typical or traditional downstream dam. We see the components. We have a core, typically impermeable core, clay, a core of trench, just to stop the water going through. We have the foundation materials. We have tailings. We have a shell that could be rock fill. It could be general fill. We have some filters just to deal with a failure mode because one of the components could fail. And we have all those components and a drain, how we're going to collect the water, how much water are we going to get through here, through seepage, and so on. Then we have variations in tailings dam for that. We have a center line, then similar components, but in some of these configurations, then the tailings might be more critical. The foundation might be more critical. The rock fill might be more critical. The filters might be more critical. And that is part of going to that journey of what is critical based on your failure mode. Then we have a traditional upstream construction. Then you can basically infer from here where, hold a second, this is sitting on tailings. Then are the tailings the critical element to test in here? Is the rock fill in here? Is the level, the phreatic level? Is the water inside? Then we go with a traditional downstream construction. And it might be that in this one, well, I don't really care about the tailings. Then the tailings are not that critical in my case. The foundation might be, the rock fill might be. Then just basically trying to answer that question. I mean, what is what we want to test? And typically the answer is what is important to you to test. I would have thought that if we have a dam and it's going to be made of rock fill, and the rock fill is a component, it's a really important component for the stability, then you want to understand what rock fill is made of. Is a rock fill made from a really hard rock, from a basalt, a monzonite, or is really made off of a really sedimentary rock like a sandstone that you can break and damage really easily? Then you want to understand that because you're going to rely on that material to maintain this dam stable. Is your clay, if you have a clay core, is that a clay core is actually made of a good clay? Can actually the clay be impermeable? Is the permeability what you are expecting to see? And if you have a filter, then is the filter actually able to dispose water? It's actually permeable enough, which is the opposite of your clay core. Can the filter actually collapse if we have tunnel piping and so on? Then the tailings, if we have a configuration like this, are the tailings can liquefy? And I have all my dam basically sitting now on tailings and potentially could liquefy. Are those tailings, if I have that dam, are the tailings gonna go and disappear under a seismic event or start liquefaction? Or no, they're gonna actually deform nicely and happily over the next 30 years. Then that is basically in my sort of a short summary, what you need to understand, what you want to test and why. Then I'm just gonna start with something quite, I think, simple, but to me is the key of everything that we do. And as geotechs is the heart of what we do, because everything that we have in a dam, they have or complying with these 3 elements. Actually, there are 4. Typically, we ignore the gas, but I go into that for a second. Then when we have some sort of a voids, we have air. That is a typical cross section of a soil. Then we have water in there that move, and then we have the soil particles than that. Then a tailings dam or a dam, a more a tailings dam, is a beast. I see as a beast and it's alive. And when I say it's alive, is this in here changes as you build the dam, as you add to the dam more weight, you add more water, you remove the water, then that will change how this material looks in the inside. And this is exactly the same for the foundation, for the rock field, for the tailings, for the filters, pretty much every single component follow these three rules. Then if you add weight, then the water is going to try to get out, the voids will disappear, then you have a material that potentially is more dense. If you're making that material more dense, are you making that material now brittle? Are you making that material actually being problematic? If you, in the opposite, if you remove weight, the material actually become more loose or looser, then are you creating a problem? Then you really, is what you're trying to do as a geotech is trying to understand this relationship through the life of your dam. I mean, how that's going to change based in the way how I design, operate the dam, how I build it, and at the end, how I close it. Then it will change. And we're going to go through ways to basically understand that change. What I mentioned, and I'm not going to talk about gas, is something else in here is in really rare or not common cases, we have gas as well inside here that David mentioned early today. You can have a gas that could create combustion, or you can actually have gas that changes all this. It's a mine that I can remember right now is in PNG, in Lihia. It's next to a volcano, and we have gas. That is gas in there, and it's that steam because it's coming from the volcano and the heat and creates another complexity. Then in that instance, you probably want to check for gas. Another example that I have is back to my homeland in Venezuela is that could change simple with ants. Then it was a dam that was being built, and they have these really big ants, and the ants were eating the soil and leaving big cavities. Then we are actually even building or changing things. Then you have a piece of insect in there that was changing these properties. They were creating basically more voids, and that make the soil potentially collapsible. Then going through ocean bases in what Manuel basically mentioned, I'm not going to try to go too deep into the soil mechanics. It's basically, as a geotech, we're trying to understand these two things. Where are we sitting in this curve? And I like to explain this graph. I'm always trying to make it in a simple way. This in here, or what we call the radiatory stress, is the force that you apply to your dam as you are building, operating your dam. And in here is, we call it a strain, but it's really the deformation. Then as you are adding weight or removing weight, the dam will deform. And the way how it deforms, then it will actually tell you how critical the material is. Then some instance, what we call brittle, it doesn't deform much. Then enough force will actually make the dam to break really rapidly. The other option is what we call ductile, which is what we really like to see, is basically flexible. You can add weight, remove weight, and start basically flexing through the life, and then you can see it, you can wash it, you can see cracks, and the cracks could be there for 30 years, and you don't have a problem. Then back in here, this is what in this region is the region that we don't want to be when you are looking at this, because this actually could happen. It could happen really fast, and this is the region where we want to be, which is what we call the safe region. And in some areas, this material looks like this, which is all perfect. In other ones, looks like this. And in other ones, the material that looks like this to start with, then by the time that you put another 30 meters of rock on top, it becomes like this. And that's what you need to understand, how this beast is going to evolve over the life of your facility. Then why we want to test it, I'm just going to go through simple points in here. We want to design. We want to understand what we're going to design against or for. During construction, we want to predict how the material will behave. During operations, is pretty much it's another phase of construction, but typically how, as I'm operating the dam, how it will behave. And closure is after we close this facility, how it's going to perform over the year. Now, how we do it, and basically we have two simple methods of ways to do it. Most of the time, we have to do them in combination. Then we have in situ testing. Then typically you go there, drill, take samples, do in situ testing, CPTs, SPTs, shear vein. And the other one is actually go there and try to collect the sample the best that you can and test it in the lab. The problem with the two is this one in here, we don't really understand what is going on in the ground. Then we rely on correlations. We rely on, if we put a bar in the ground and hammer the ground, then when that compares to another bar in the ground that was done 30 years ago by a person somewhere else, and yeah, it makes sense. It's the same thing. Or if we actually go to the lab, then we collect a sample that is really small sample and trying to mimic the conditions that is in the ground, which remember, we don't really know those conditions anyway. Then we're trying to assume the worst case scenario. Then typically you need both. Then I'm just going to go briefly to just the most common ways to do it. And in terms of in situ testing, we have the basically SPTs. You go there, as I mentioned before, you hammer the ground, and somehow you count how many times you use the hammer, and you basically trying to work out a density. Then, okay, my material is dense, is loose, and then you relate or trying to link that density to back to what I mentioned before is how many voids, how much water I might have, what sort of a soil I have, and then you correlate that through those areas. Now, something interesting about this testing, and I'm quite familiar with these scenarios. I don't know about in India, but in saprolites, really all residual soils. In Australia, New South Wales, we have that. You go there with this tool, to start trying to hammer and trying to get the rod down into the ground, and you can't, because the soil is that hard, because it's basically been going through leaching. It's really hard, but guess what? The material is super brittle. Then it will break really fast, really quick. And you think that you are in really nice, hard soil, and you are not. Then that is where you need to complement that. Probably one of the most popular techniques in tailings dam is the CPT. It's quite similar to the other technique. This one goes as a bar, go faster. It's slightly smaller. You measure the pore water pressure, and then you basically one more time use empirical correlations and trying to work out the soil conditions, the layering, where the phreatic level is, and so on, and the liquefaction potential as well. Another simple or common tool is your shear vein, which is pretty much similar to the other techniques. You push it into the ground, you rotate this vein, and you're trying to basically correlate that to some sort of a strain. Typically, you basically use this to determine on range. If we keep going, and then another one that is typically common is the permeability. As I mentioned before, it might be that we are concerned about water going through the foundation, how that water it might impact or core or the rock field. Then this is basically a packet test, which is simple. It's a borehole. You have different configurations. This one is a double, and then you're trying to put pressure, and then the water goes through. You're trying to go either side, and then you can work out the permeability of that material and say, well, if I put all this weight and all this water, the permeability of that material is this much, and the water can go really fast through there, or it can go really slow, and then you basically put that in your design if it's critical. Then let's go to the other part, and that is about the lab testing. And in terms of lab testing, is a number of testing, and it's quite really advanced. It's quite simple type of testing. And all of them has some pros and cons, but in general, the most common ones is this one here, is the direct simple shear. The idea is that this shear the soil either side, and trying to make it more like an horizontal type of failure. Is becoming quite popular in the dams industry. Something based on my experience, I can tell you right now, this doesn't work for hard soils. The hard soils, it tends to basically slip through the connections, and it doesn't actually give you a good result. But I think that this is becoming really popular, really good for clays, soft clays, or medium stiff clays. Really difficult to use when you're dealing with hard residual soils. The most common one of all of them is a 3-axial test, where we're trying to actually mimic the opposite, is just actually mimic when we are loading the soil, or sometimes we pull the bars up, and this is the way how we are basically pulling the soil, or what we call extension. You can get drain values of the material. You can get consolidate on drain as well. Then you're trying to understand what happened when you basically load the materials, how we respond, how we'll compress, how the dye density will change. And the idea is that you basically do that for the full design. Don't actually do it just for one stage, trying to go to a closure level. And typically the problem is on the mining industry is you start with a dam that's supposed to be 20 meters high, and you end with a dam that is 100 meters high. And then most of the common errors is they forget to check this, and they just keep using the same values than they had for the 20 meters dam. And it might be then the whole thing changed in between 20 and 100. Other one is not really as common, and this is just a variation of the other triaxial, and this is about cycling. Then you just go up and down, up and down, up and down, and trying to mimic what earthquake will do to the soil, how it will react. And it's some variations. These ones go up and down. We have only other ones that go sideways, similar to the direct simple shear test. In terms of permeability, I just it's few options in here, but I just use this one just to give an example. Then it's a permeameter. Then similar thing. We want to understand, okay, what is the permeability of my sand? What is the permeability of my clay? What is the permeability of my foundation? How that will impact my my dam. Then what happened next? Now we went through, we collect all the samples. We determine, well, I want this material to look like this, and based on my lab results, I'm expecting to see the phreatic level to stop here, go down, and disappear in the foundation. Then, if that is the case, and I want to be sure that that is the case, then during construction this is empty, then I might not put any instrument to look at that, but during operation, then I want an instrument there, because I want to be sure that the permeability is what I assume it will be. Then during construction, you basically allowed to put that piece of instrument in here, because it's really important for your design to understand that permeability. Then now you have something you can use to understand what you're looking for. Then you have the permeability, you can predict where the water is going to be sitting, and you design your instrumentation to match what you assume. The big surprise is that never is exactly the case, because you just test probably a third of all the clay that you're going to use. Then you rely on the contractor to place this in layers in a way that actually you achieve what you are after. And even well-built dams, you're never actually going to get exactly what you want. Then that's the reason why you put the instrument. And then during operations, you can actually verify that what you assume is actually the case. Another example here, the foundation. Then, well, my foundation is brittle. I know that it's brittle. Then I need to design for that for that response. Oh no, my foundation is ductile, but I'm gonna put in here a shape array, an inclinometer, because I want to be sure that as I'm putting weight in here and this is going up, because remember, we just grab a small sample, probably every 50 meters of a dam, that could be 5 Ks. Then for sure, we're gonna miss something because it's a lot to test. Then you want to be sure that you are looking and verifying what you are doing. Similar with your filters. Is my filter able to actually drain any water? Then if this failed and I'm wrong, and I basically, if my filter is actually working, then you might introduce another one here. Similar with the zippers. Then you start now thinking into, okay, how I can actually use, and how can I use, and what I'm going to use to design my instrumentation. The settlement, okay, I put the sample in a triaxial and I notice and it settles this much. Then okay, then this similar thing should happen here, an odometer test. Then that is basically the way how we actually need to link this. Then what happens is you go to the design phase. You actually understand now the shear strain. You know what the material is going to look like. You know the permeability, and you know the compressibility of that material. Then that is the moment when we're at that design stage. We actually add all the tools that we want to add. And the problem is, it's not common that we are actually able to go into a design phase. Typically, we go to a dam that has been there sitting for years, that nobody actually have done the geotech. and nobody really understands the failure mode because the dam is quite old and you don't have the records, then you basically, this is the same, it's similar, it's valid. Then you need to start actually looking for the right things to look for. Then how you do that, and back to what Malcolm was talking about, is your failure mode. Then you have a dam, it's existing, then you really want to understand what is critical, you do the testing and you work through that. During construction, some of the dams, it's more common probably in water dams, they fail typically when you start filling the dam. This also could happen in tailings. And as a way how you're building this, and then you want to understand what is critical for that construction phase. And even though the instrumentation that we use is the same, and what we are probably going to be looking or monitoring for is the same, because we're going to probably be looking for permeability in the clay core. Then one thing is permeability in the clay core during construction, during operations, during closure. Then it's a different value. And that is the reason why I say this is a beast that is alive, because it's always evolving. And it's evolving based on the way how you manage these dams. During operation, it might be that you are looking more, well, what happened with the pressure, how I'm increasing the pressure because I'm putting all these tailings full of water in here, how the seepage is actually acting in here, ongoing compaction, the material doing to settling. Then what you are actually using is the same, but one more time, it's the same, but it depends on what part of the cycle you are. And that basically are the key. Then we go for the final one, which is your closure. Then in closure, I'm expecting, well, the water will disappear, this will consolidate, everything's going to look nice and pretty. Then you need to be able to actually look that as well. And then by then you have a different trigger levels, you have a different criteria to assess. And basically that's it. I hope by trying to make it simple as possible, just to make you think into how to use the data and you collect in the field, and how you can use that to develop your failure modes and your monitoring.
I'll take it. Don't go away, because we've got time for a couple of questions. So has anyone got some burning questions for Edgar?
Yeah.
Good.
About liquefaction, you need to understand what is the actual density down there, what are the in-situ pressures and stuff.
And
How can you
now liquefaction is one of these things where everything that we do is based on empirical correlations. Then you either have or not have liquefaction. Then the few things that you can do about liquefaction is trying to understand if you're going to have liquefaction, and if you do, my advice is you design against that. Then in terms of monitoring, then it's a certain amount of acceleration, then it will trigger that liquefaction, and you might install seismic sensors and understand how that works. Leandro, which is over there, he can probably add some value on that. He's involved in a dam where liquefaction and seismicity is a big problem, and they basically look after that quite well and deal with some big earthquakes, and probably Leandro, but that is what you need to look for. I hope I answered the question.
I will work one thing. How do you measure the residual strength at your tailings? What are the different tests?
Look, in terms of residual strain, you have what they call now the state of the art, and you go now with the critical state testing. That is the flavor of the month at the moment, where you're basically trying to predict at what point the soil is going to reach the critical state line, and at what point the soil have the constant volume, and without any extra shearing. Then that is at the moment and then you have a lot of people trying to collect samples and trying to mimic what they are getting from the CPT and the state parameter, go there and the void ratio is about this. Then we put it in the lab and we test it and we get the residuals. We got a residual value that looks like this. You have a shear vein, they go down, they rotate it, and they got another one. And look, at the end of the day, if you rely on that for the dam to be stable or not, it's going to be really difficult, because you go to all these experts and they say, yeah, that is fancy, it's nice, it's a state of the art, but the correlation that you do using a CPT or an SPT is telling you that you're going to go to 0.0000. Then it is evolving. We are learning more, but rely on that to design is basically not a good practice. Rely on that to understand how your dam is going to perform during a seismic event is different. Then because then you are trying to understand, okay, how much it's going to shake, how much it's going to crack. You are not trying to basically understand it will fail or not, because it's more likely than if it's liquefiable, as Morgenstern basically said, it will liquefy. And if you rely on the material not to liquefy to be stable, then it's highly likely that it will fail.
One last one up the back there.
There was one question, what could be much more dependent, the field test or the qualitative condition?
What is, sorry, couldn't hear that?
What should be more representative, the field test or the laboratory?
You use both. In some depends of your level of comfort in terms of how you collect the data. Sometimes you cannot collect good samples, and then you need to rely on in situ testing. Sometimes you can actually collect good samples, and your you can actually create your own correlations, and the data from the lab testing is quite good. Then it depends on the case where you are. If you are in a sandy environment where the tailings are quite sandy, then it's no ways that you're going to recover a sample and you completely change the properties of that sample. Then you need to trying to predict or trying to guess or trying to use engineering judgment to mimic what you think the sample is under. Then you rely more on your in situ testing because it's the best practice. In other cases, you cannot actually do in situ testing because of that example I mentioned in Australia. You're trying to do in situ testing and the tools that you typically use don't work because it's too hard. You cannot push a bar or do it. Then it varies.
Comments. Quick.
Okay.
Number one, to the question before. Check that website, tailings.com. 4 universities, 6 mining companies working for 4 years or 5 years. They did progress a little bit in understanding static liquefaction, but we have more information, but we also have more questions. And secondly, maybe you want to mention quickly to the other question about the benefits actually of sonic drilling.
Yeah, that's probably
For sampling.
yeah. Well, benefit or no benefit, it could be. That is one of these topics where sonic.
There's more benefits than
when you're trying to basically, for the ones that are not familiar, sonic goes through small vibrations, and then you push it through, and the idea is that you don't wash your sample. Those vibrations, even though they're small, you create some sort of disturbance. I use sonics a lot of times, believing that it's gonna get the best sample ever, and actually, that was trying to use residual soils and completely smashed the sample. I use it in tailings, and you can actually recover the tailings like pretty much a slurry. It liquefied the sample. Then David Williams used to say, if you are able to collect a sample from a tailings dam in good conditions, it's highly likely that the tailings won't liquefy. Because if it's the only way that you can record almost a good sample is they won't liquefy, because whatever you do, it will change it. Then it's sort of a, but sonic is another technique, and you actually can get good recovery.
the points using water.
Yeah.
Proves up everything.
That probably is something important. What I've seen in some areas in South America and in sonic is not really common. And I've seen people actually going through clay core with just diamond drilling with high pressures, destroying, potentially introducing a crack to a clay core. Then sonic is actually quite common in Australia. It's seen as well in Europe, but it's not quite common in Brazil, in Chile. They don't even know that sonic rig actually exists. Where you can actually just not introduce water and collect a good sample of a clay core. That probably is a good example where you can use it quite successfully.
All right. Thank you very much, Edgar. And of course, if there's more questions, we might have time later, but also you can catch up at lunchtime and talk. And I guess I'll introduce Annika, and I was really a bit shocked when we heard that the CDA failure modes only considered 2 things: overtopping and stability. But we often, as geotechnical engineers, we quite often forget about the environmental failures as well. And like in Australia, like if you've gone to the what's it called, the I can't remember the name now, but website related to nuclear industry, but it's got a schedule of tailings dam failures that go back to 1965. Anyway, one of the only Australian examples on there is Olympic Dam, which was basically seepage failure and a lot of acidic water seeped into the foundations of the dam. So I'll pass over to Annika. Annika's Director of Tailings Consultants Scandinavia. She's had a long experience of 30 years in tailings management, which really started with her interest in closure. And she did a state-of-the-art report on water covers closure for tailings dams through the Luleå University of Technology in 2005. But most of us will know Annika because of the great work she's done over 24 years, coming on to 25 years in ICOL in Committee L, and she's been involved in a lot of the tailings, a lot of the bulletins that we've done over the last 24 years. So welcome, Annika.
Realizing that I might not have prepared 100% and now having two computers. Yeah, I'm going. I don't know how I can get the Mentimeter questions on the other one. So but I think I'll do it this way. So I'm going to talk about environmental performance, and that sort of include how do we confirm the environmental performance, which relates to oxidation, acid mine drainage, water quality, seepage, geochemistry, and environmental failures, etc. And the more I started to think about it, the less I kind of felt I understood. So I'm gonna have you working a little bit now. So good environmental performance. My suggestion to sort of define that is zero harm, that we have no short or long-term effects on the environment or harmful effects. And that brings a little bit of questions. So that was a strange order. So I have these 4 questions. So if you use that barcode, QR code, or you can also log in on mentimeter.com with the code there. I just need to get this. Do you get the question or? So I need to activate it here. So it's activated?
Yes.
Yeah. And then now it would be very fancy if you could see on the screen whatever answers pops up, and that's my problem. Because this that I only have on my own computer. Yeah. I know. So what I will do when you receive the PDF versions of the presentations afterwards, I will include all the results. So I've got 4 words from 2 people. I hope to get a little bit of some more words. It's allowed to write more than a word as well, but the shorter, the easier to see the result. I'm not so used to using this Mentimeter. I've been in the audience and not not the organizer of this.
This presenter hasn't changed the slides yet.
Okay, it says so. Then I Let's see how I can.
We kind of answered just the first one.
Yeah, and then you need the other one. Ah, here it comes. 56 responses. So now the second one question should be.
Ignore it.
Yeah. So the second question is sort of what is the sort of zero level that you should compare to when doing a site location for a new facility? You look at different options and you compare to sort of the zero alternative is either an existing facility or no facility at all. But when it looks to when you look at what you compare your environmental results to, what time in nature should you compare to? Nature is evolving the whole time. And nature is affected not only by a mine site, but other things around. In Sweden, reindeer herding is often in conflict with mining in the northern part. And reindeer herding has changed over time. So maybe how they used to do it is not. In the old days, the reindeers always walked themselves. Nowadays, they transport them on trucks, sometimes from summer to winter feeding. And maybe then the walking part is not so disturbed by mining. But still, the reindeer herders don't want to have the mines in areas which they used to use before. And maybe they want to use them in the future as well. But what is, when it comes to environmental monitoring, what is the base level? Often we also monitor with water quality upstream the facility and downstream, and try to see the effect. And maybe things changes upstream.
And reindeer one,
Yeah.
that would affect the reindeer's ability to survive. To some extent, they're being trucked instead of making that long walk and surviving. You're changing the whole climate.
Yeah.
Bad.
But that's they're missing that walk, but they're walking around constantly at the summer feeding and the winter feeding.
You'll have to make a separate presentation on how they catch the reindeer.
Yeah.
I'm sure it's very interesting.
Yeah, so I've got 49 responses, and move on to the third question. So it relates a little bit to the other one when in time. I can read some of the words as they come up. Before, after, during operations, assessment in time, before construction, constantly. It's quite much the same words, but just differently phrased. There's still 43 responses. I'll move on to the last one. Who is to decide what to monitor? there are some discussions in Sweden regarding this where that there is different opinions on what to monitor and threshold levels. So DOR, EOR, environmental engineers, government, surveyor, managers, designers, authority, owners, specialists, company. So kind of a split view on this. Who is to decide from the owner to different people involved during with the facility and the up to the government. So it's not that easy. I find it. There is quite a spread of these of the results that you gave. I need to figure out how to get. Yeah.
Annika, you want to share what you're looking at?
Yeah, is that possible?
Send you a meeting invite on Teams to your email address, and then you can just share your screen.
Yeah, and I don't have so much time. I see David is.
Holds the whip.
Yeah, you haven't sent already.
We're doing what's
Yeah, I keep on in the meantime.
Pass your computer around.
Yeah. And now I cannot change slide. Is that me doing something wrong or?
Another way to do it on the.
Yeah.
Maybe
That's it.
share a different screen.
That's it.
Yeah. Okay. Yeah.
Another blind slide.
Yeah. So then I need to figure out how to do like that.
Okay, you should get the meeting invite now.
And I hope you get access to, yeah.
No, okay. You got it. Get a meeting invite?
I need to connect my computer.
You are not connected on internet.
No, yeah, I'm connected on internet, but not to Teams.
Yeah.
And I haven't got.
You received the invitation.
No, I haven't.
Well, if you want to sort of.
Yeah, so that's. Yeah, so some responses are coming in. The pollution, dispersion, contamination, seepage, effect on biodiversity. Maybe there should be more. Right? I don't know what happened.
Do you want to sort that out that we can start the other exercise?
And then you can.
Yeah, and then I can show these. Yeah.
Right, so we'll take a bit of a break from that while Annika and Edgar kind of sort it out. And we'll now go on to this instrumentation exercise. So you all, there is a presentation for that, Edgar. How do we get out of this one and start another one?
I'm making a mess here.
No, it's. Now you should probably actually come into the room.
Okay.
Section 4, short course is not the same. Design exercise.
Yeah. Okay, so while Annika and Edgar are sorting that out, maybe hopefully we can have a bit of time on this exercise. So basically, you've got a handout sheet, and here you've got the predominant hand. This is an exercise we're going to be doing throughout the next couple of days, where we're going to work through and improve our surveillance and monitoring plan for this significant tailings dam, which does exist, but you don't know where it is, hopefully. And the idea is that there is a prize for I think it's going to be for the most engaged designer who puts the most effort into the exercise, and we're going to be spreading into some groups. That was the plan anyway. It's just not the best room for it, but maybe we can end up with about 6 groups. Maybe, this people here onto that corner, and you guys in the middle over near the door, and the guys at the back up near the back corner, and then and the same here. There's probably a group around Pierre here. You guys probably in the back row there can all get together, and the people who are presenters, and particularly guys like Edgar and Malcolm, can be roving mentors. I want you to basically discuss amongst each other just the question we're going to come up with. So first of all, we've got a dam. It's a hard rock mine, hard rock tailings, 80% passing 75 microns. So it's a pretty fine tailings. This comes out as a slurry, 50% solids, and there's spigots all around the perimeter of the dam. There's a central decant, and the idea is they're trying to create a beach that degrades into the centre at the decant, and there's a pond there which they'd be wanting to minimise as much as possible. And the whole idea is to have a spillway down in the bottom left-hand corner there, which is controlled. The invert of the spillway is controlled so that the level is always below the minimum level of the tailings beach, and so they put a lot of effort into keeping the tailings beach at the same level all the way around, so that maximises their storage for stormwater without the water actually contacting the external embankment. The rise rate is 1.8 metres per annum. It's a tropical climate, so they get cyclones and wet season, and then a fairly long dry season. And they've got upstream construction. And you can see from the cross section, there's been a starter dam, then upstream construction, and people have suddenly realised, oh, hang on, what's going on here? We might have a bit of a problem, and we have to build these buttresses. So there's some buttresses that have been constructed. And so it turns out the design, really the design case is the post-earthquake liquefaction. So you've got different types of tailings there, starting with the historic ones that are pretty low strength, and then improving until you've improved the quality of the tailings as they've gone up. But there's a slip circle there that you can see, pretty hard to see, but you can see it goes down into those deep tailings where it's more prone to liquefaction and much weaker. And that you can see where the buttresses have been built to contain that slip circle. So that's the background. And the first question we're going to talk about today is failure mode assessment. So let's turn the page over. Question 1 one is credible failure modes. We want to try and come up with some credible failure modes. List them on the left-hand side. Also think about the method of detection or warning. What would we put in as a detection system and maybe a warning system, and then method of predicting is another column there too. So if you could form into some groups, maybe we could do yours when we come back after lunch, might be better.
Yeah.
But then we can just have these groups talk amongst yourselves. We have some roving mentors, and then our lunch is scheduled for 1 o'clock, which is in 15 minutes. So we've only got 15, maybe 20 minutes to talk about this together, and then move down to have lunch. And then that's it. Is everybody happy with that? All right. So if you can form your groups and have a talk about it. And the roving mentors who are the presenters can see who in the group is performing enthusiastically and note their name. 5 or 6.
Create a group in here of 5 or 6. I'm going to look after the group here. Thank you for volunteering.
Yeah. And maybe if you could mix up, don't just sit with your colleagues and your people you know, maybe move around and get into another group with different people.
Yeah, we have.
Hang on. I don't want you to worry too much about the detail of those materials, and that's not really important. The critical thing is there is a failure, potential failure through the tailings, and okay. Okay, thank you, Nancy. All right.
It's an Australian structure, and then all the were added to it. All this
The cross section. There's a good reason why.
But the real stuff. Over talking about things and then. Right, I'm not going to give it some. I'm dealing with how. I can see
So then we have to decide how. Oh, we are right or wrong.
Okay, well, we write one and then we talk. Let's put one.
Since our screen ourselves into the really construction.
Maybe this.
We don't work.
These lines.
Then I don't have this type of presentation.
Because of the height. Still seconds. We go to the spectral accelerator. You can make it.
Have five, but why not? Yes, we don't know these guys, right?
The other thing is, you do these, you really break it down to walls, as you say. Based on the data, even if something. You need a step. You can use the same type of framework, but a different section. So, you can make it
Section.
Starting. That way, I find that. Very clear.
Yeah. It's good.